So our first speaker is Dr. Archana Arbind from the Indian Institute of Technology, Kharagpur, which is well known as the IIT in India. She is a faculty, early career faculty member in the Department of Mechanical Engineering there. Her background is in the computational mechanics, especially focused on the higher order theories for the beam and plates, rods, and the cells, in the classical and the Cosserat continuum. And currently, she is applying those tools with biomechanics problem as well. After finishing her undergrad from the IIT Guwahati, she did her graduate studies from Texas A&M recently, and before joining the IIT Kharagpur, she also did a postdoc here at Texas A&M in the Department of Mechanical Engineering. So without further ado, let's welcome her. And today she is going to talk us on her recent work on the general higher order one-dimensional and cell theory for the pipe-like soft structure using the orthonormal moving frame with potential application in biomechanics. So over to you, Dr. Arbind.
Okay, thank you, Manish, for the introduction. And I'd like to thank all the organizer for arranging this wonderful series of talk here in this platform. And is my screen visible?
Yes.
And am I audible?
Yes.
Okay, good. So let me start with my talk. So today I'm going to talk about general higher order one-dimensional and shell theory for soft tubular structure using orthonormal moving frame with the potential application in biomechanics, especially in arterial mechanics to be specific. So let's dive in straight to the topics. So yeah, can I? Okay.
We still see your first slide, at least on my computer. I'm not sure if it's my issue or.
Okay, I'm trying to remove this bar of Zoom. Do you have any idea how to remove it?
Oh, by the way, for the bar of the Zoom, it's very hard to move it. You just move it to a place that maybe you think will not hide your content. That's usually how I do things. Maybe the left upper place or left bottom place, I usually move them there.
Okay.
But there's no way to get rid of them. Yeah.
In that case, I'll not put full screen, then it will not abstract. Is that okay?
Yeah.
Okay. So, yeah. So I'll start with the one-dimensional theory. So the aim here is solve the large deformation large deformation of the wall of soft tubular structure. So here we can see that there are in literature there are lots of Cosserat based rod theory, which is kind of a director based theories, where the main focus is to model the center line deflection of tubular structure or rod structure or thin rod. But in some of the work, they do try to model the whole deformation, as in the wall deformation as well, by rotation function and warping function. The problem with this approach is this rotation function and the warping function is not unique. So to overcome that, in this work, what we have done is take a cross section and approximate the full deformation of this cross section by a general basis function, and then reduce all the governing equation to one-dimensional ODE. And other advantage of this kind of approach is like if it is a hollow tube, we also have a domain transformation rule. So we can couple the fluid flow like blood flow with deformable wall with this kind of approach. And in that way we can do couple fluid solid interaction problem in tubular flow via convective coordinate system. So let's talk more about one-dimensional theory via this approach. So yeah, so we see in all these kind of structure, we have a space curve as a backbone of these kind of a structure. So first of all, we need to map such a structure geometrical. There should be a geometrical mapping system, and to map these kind of structure, first we need to frame the central like reference space curve. So there are very commonly used frame for space curve is Frenet frame. So it is shown here. It is a local frame. So T is at each point there is a triad, orthonormal triad, and T is the tangent. P and Q is normal and binormal, and it varies along the curve by this rule. This is called Frenet formula, and S here is the arc length coordinate, and K is curvature and tau is the torsion. This is a pretty old. It was first proposed in 1847, but the Frenet frame has some problem. Like for example, if there is a curvature is 0, then this frame is not defined. Similarly, here also the curvature is 0, and the point this point is a point of inflection. So there is a jump discontinuity here as well. These are smoothly joined different kind of sections, but the frame would be again discontinuous. So this discontinuity problem gives us a lot of trouble if we try to do FEM or some geometrical mapping via this kind of frame. So what Bischoff did is he proposed different kind of frame called Bischoff frame in 1975. So it solved discontinuity problem. Bischoff frame is minimally rotated from frame. So that means it varies like this. Here M1 and M2 is the unit basis in normal plane, and T here is the tangent vector. So and it varies along the curve like this. And here K1 and K2 are the curvatures, and there is no torsion. Torsion is 0. So this is what Bischoff frame is. But Bischoff frame, one more advantage of Bischoff frame is that it can generate it discretely. So for all kind of numerical method, it is very useful because we don't know the equation of central curve. Most of the cases, we get it numerically. So for example, if we want to do iota or something, so we get the geometry from the scan, and then we like segment the geometry. So in this kind of problem, Bischoff frame would be very useful. But Bischoff frame has one problem, that if there is a completely closed curve, there would be discontinuity at the point of closure. So this discontinuity we want to remove, and for that purpose, we propose a new kind of frame, which is called hybrid frame. So in that, what we did is to close this gap, we gave a continuous spin to Bischoff frame along the curve and close this curve, and then the resulting frame would be hybrid frame. So there is no discontinuity in hybrid frame. This is the most general kind of frame to frame any space curve. So how this frame will vary is by this formula here, K1, K2, K3, all three component would be non-zero in the Cartan matrix. So this can be specialized to both known frame like Frenet frame and Bischoff frame, but hybrid frame would be very general one. Okay, so based on this frame, what we have done is propose a general curvilinear coordinate systems. Here the coordinates are S coordinate is along the reference curve, R coordinate and theta coordinate would be the polar coordinates of each at the each normal cross section. So S R theta would be our curvilinear coordinate system. So, but at each point of the structure, we have a orthonormal moving frame. What do I mean by that is we don't take what we do in curvilinear coordinate system, that natural covariant basis we propose. That natural covariant basis actually is non-orthogonal or non-orthonormal. In some cases, it is not even perpendicular to each other. So in this case also, it will not be in general perpendicular to each other. Only for Bischoff frame, it will be perpendicular to each other, the basis vectors. But what we have done is take a orthonormal moving frame. That is what we did, like ES here is at each point, ES is parallel to tangent matrix, and then E theta and ER would be in the normal direction. So these ER, E theta and ES makes a orthonormal moving frame. So in this, with this basis vector and this coordinates, we derive all the kinematic quantity of interest. With the help of orthonormal, we see that all the derivational complexity reduced drastically. So for example, if the displacement field is US, U theta in all these three directions, then gradient would be given by this. I'm not going to, we have derived this in very detail in this paper. If one want to see, they can refer it. So further coming to the constitutive relation, we are going to solve a problem where the structure is made of soft material, soft hyperelastic material. So for hyperelastic material, the energy density function can be given as a function of I1, I2, I3, which is the principal or invariant of C, which is a right Cauchy deformation tensor. And this is a very well established constitutive model. And if we want to use the incompressibility condition, we use Lagrange multiplier method. So lambda here is the Lagrange multiplier, and for this energy density function, the Piola-Kirchhoff stress tensor and Cauchy stress tensor are given by these formula. So different kind of model for compressible and incompressible various model is this. Our formulation is very general only. It can cover all kind of hyperelastic material. We take these as an input in our program. So let's come to the displacement field. So at each point of the tube, we have approximated the displacement field of the cross section. That is, at each cross section, this phi here is so in theta direction we have used Fourier basis for basis function, and in R direction we have used Legendre polynomial. One can also use power of R, but Legendre polynomial I have used because it is orthogonal basis function, so it gives some advantage in numerical calculations. Okay, so this AX would be the matrix of basis function, and phi S here is the displacement coefficient, which is unknown and only function of S coordinate, that is the length along the reference curve, which we have to find out by numerical method. So all these bases are known. So here the order of approximation is given. For example, AS is NR and MR and PR is the order in radial of the radial basis. Similarly, N theta, M theta, and P theta would be the order of basis function in theta direction. So based on this, we calculate this displacement field, we calculate the deformation gradient, and this deformation gradient will write as a vector, like row vector, column vector, and this f tilde here is the column vector which contains all the components of uh, deformation gradient, and this phi is displacement variable which need to be defined, and G1 and G2 are defined in detail in the paper, so I have not written it here. So based on this, I have derived the governing equation for Neo-Hookean material. So this for Neo-Hookean material, the energy density is given by this, where mu is the material property. So based on this one, we get the governing equation as second order ordinary differential equations, that is only in one variable, and that is why one-dimensional theory. So this ordinary differential equation, we will solve it in finite element method. Of course, it is non-linear because the material is non-linear, as well as it is a large deformation theory. So these coefficient H and F are integrated throughout the cross section. So as I said, this is a nonlinear differential equation. So we will solve it by finite element model, and we approximate our displacement variable by this. This finite element model is 1D model. So we can use finite element model of beam to solve this problem. So here the stiffness matrix and the force vector is again nonlinear, and hence we will use Newton's method to solve it. So let's see some of the numerical results for incompressible Neo-Hookean material. And also we'll see some other material model as well. So for example, here it is a straight cylinder. Here the reference curve would be straight line. I have used this one to validate our result. So thickness and length, all the geometric parameter is given, and this is the material parameter, and internal pressure is applied. So I have solved this for 3 boundary conditions. This the first one is radially free and axially fixed boundary condition. For this one, exact solution is possible. So I have compared my result with this exact solution, and this is this shows a very good agreement for different order of approximation. And I have used also Lagrange multiplier method, and as well as the penalty method for incompressibility condition of Neo-Hookean material. So the next one is radially fixed and axially free. And in this case also, since the exact solution is not possible, I have compared the result with ANSYS cell theory. Please remember this is one-dimensional theory, and number of variable is quite less as compared to shell theory, because it is a axisymmetric case also. So U theta is simply 0 here. So in this case, our result shows very good agreement with cell theory, which is very expensive computationally. This is the third boundary condition, which is completely fixed. And here also we have compared the results for both the method Lagrange multiplier and penalty method with cell theory, and shows a very good agreement again. Here in this case, what I have done is varies the material property. Here the light red part has less stiff, like softer part, and the material property varies parabolically. So maximum mu is this 3 into 10 power 4 psi, whereas minimum is 1. So minimum is here at the center, and again it is completely fixed and internal pressure is applied, and in this case we see the deformation like this. So this kind of a structure is particularly useful to analyze arterial, like aneurysm type of problem. Okay, in this case also I have compared the results for different order of approximation. It converges very well. So this problem is not only limited to thin cell, but also thick cell structure. So here 2 cells structure are showing a cylindrical cell, which is pretty thick. and the thickness is 0.6 inch, whereas the radius is 1 inch. So these are pretty thick and completely fixed boundary condition, again under internal pressure. And this is how the deformation occurs at the outer surface. And if we want to see the inner surfaces like this. So again, in this case, I have compared the results. So for thick cell, ANSYS cell element perform very poor. So here we can see that ANSYS cell doesn't give good results, convergent result, but ANSYS solid elements, which is 3D element, which will give very good result, but that again is very expensive. But in this case, our analysis, we get result as good as 3D element of ANSYS. Here is the example of, again, straight cylinder for Saint-Venant-Kirchhoff material model. Three cases are discussed here. Cylinder under internal pressure, pinch cylinder, and half cylinder with point load. So all these three cases, again, I have compared the result with 7 parameter cell theory and ANSYS, and the results are very good agreement. Please remember, these are solved by only by one-dimensional theory. Again, this is a sinusoidal pipe. Again, under internal pressure, this is the deformed shape. And I have compared the result for increasing order of approximation. It gives good result for inner and outer surface convergent results. This is a distorted torus kind of tube, which is completely closed, and only this blue strip you see is completely fixed. Inside surface can move. So in this case, we again apply internal pressure, and we have to analyze this. In this case, we cannot apply the Bishop frame as it is discontinuous, so we go for hybrid frame. And this is the deformed shape under internal pressure, and this we have shown the convergent for dense mass as well as the approximation order. So as we see this till this point, we have used one-dimensional theory. So using orthonormal moving frame, and we noticed that with orthonormal moving frame, the derivation and all the calculation becomes the complexity of formulation reduced drastically, because we don't have to deal with non-orthogonal basis vector in general. So hence we thought we apply that for shell theory as well. So next we worked on general higher order shell theory using orthonormal moving frame. So let's talk about that. So let's first talk about a little bit what is the current state of the art in computational cell theory. So in computational cell theory, what we do is that we have a parent element, and we approximate this geometry of the reference surface in the physical space by a function, and we use the same Lagrange function as we use the approximation. That means it is an isoparametric approximation of the geometry, and this xi1 xi2 here becomes the basis for the curved surface patch. And in that, hence is in this point, all these xi1, xi2, and in the normal direction we have xi3. This makes a basis vector. But this is not necessarily normal or perpendicular to each other. So this xi1 and xi2 could be non-perpendicular to each other as well, for in general geometry. And other thing is like we can use a spectral interpolation function in finite element, which gives seem to give very pretty good results. So this is the current state. The question is, where is the scope of improvement? So if you see all these tensor based cell formulation for computational cell theory, you'll see there is a large number of terms in stiffness matrix due to the general nature of basis vector. We can reduce it by using this orthonormal moving frame. That is what we have done it here. And the other thing it includes is higher order cell theory. So for if we want to analyze soft material which has thickness stretch as well, so we need to account for thickness, like displacement in thickness direction. So we cannot just use the classical cell theory. So we have to go for higher order cell theory. And also higher order cell theory is numerically very well behaved, because it reduce this Poisson's locking kind of behavior in shell, soft shell analysis. So that is what we are going to do in this work. So let's talk about a little bit orthonormal moving frame on the cell element. So in this case also, we take a parent spectral element and we map this to a physical element by isoparametric function approximation only. Here in this case, but you see this E eta 1 and E eta 2 are not perpendicular to each other. So what we will do is like we'll take E eta 1 and normal to this surface as basis vector unit normal, and we'll take a cross product to get E eta 2, and that way we will form a orthonormal basis vector, set of orthonormal basis vector. Here we can see it clearly. Eta 1 and eta 2 are the surface coordinates, and thickness coordinate is zeta. So here orthonormal basis vector, we get it in a similar fashion what we get in normal covariant basis, but normalize it. These two are same as normal covariant basis but normalized, and the E eta 2 we get it by cross product. That way we will make a orthonormal set of basis vector. So why cartan moving frame is more efficient? Let me talk a little bit about that. Any tensor is represented in natural covariant frame is like this. Some one representer could be completely contravariant component or completely covariant component or mixed form. And in this system of representation of tensor, all these operations are given by this. Here Gij is the covariant metric tensor. So you can see there are 9 components of that. So you can only imagine how many terms are there in this full representation of this. Here the determinant becomes even more complicated, and we know in the all the models of hyperelastic, determinants play very important role. So but in cartan's moving frame, what happens, all this representation is very similar to what we do in rectangular coordinate system, but only difference is here Eij, Ei and Ej are the basis vector are not constant, but it varies throughout the space. So we have to take that into account. Otherwise, it is very similar to what we do in rectangular coordinate system and rectangular Cartesian coordinate system. So that is why the formulation becomes a little bit easier. Okay. So in this case also we propose the coordinate system. Here the surface coordinate for the tubular surface would be theta and s, and thickness coordinate would be eta in thickness direction. And here the orthonormal basis vector is given by this formula, and we derive what is E theta, Es, and N in terms of the hybrid frame, basis vector of the hybrid frame, T M1 and M2 here in this case also, and all other parameter radius with radius variation with respect to theta and S is given. So all these things are given for a given geometry. So it can cover a variety of geometry, like for example, tube with constant radius, tube where radius is varying with S, or radius is varying with S and theta both. And here in this case we can see, so problems like aneurysm we can analyze. It comes and these kind of that geometry comes under this geometrical mapping system very well. Other thing is like we can analyze all the surface of revolution very easily. Here reference curve would be straight line and radius will be varying with S, the S along the reference curve or straight line here. So in this case also, since it is a cell theory, we approximate the displacement of the normal line at each normal line of the cell surface, reference surface. So in this case, the approximation basis function would be function of zeta only, the thickness coordinate. And for this zeta, we can take Legendre polynomial or power function here in this, as shown in this case. And M, N, M, and P are the order of approximation. And here the displacement variable, which is the coefficient of these basis function, are to be calculated numerically via the method of finite element model. So if we set the approximation order as n equal to m is equal to 1 and p is equal to 2, then it will give us 7 parameter cell theory. And similarly, if we set it all as 3, it will give 12 parameter cell theory. The difference here is again the use of orthonormal moving frame. So if we use that displacement field from the energy method, principle of virtual displacement, we can obtain the governing equation as this, which is partial differential equation in 2 dimensions. Here all these phi displacement variable are function of the surface coordinates, and H1, H2 are thickness integrated values, which is given by this. So again, we will solve by weak form finite element method, and here the displacement variable is approximated by this rule, and we follow this general finite element formulation, and then the stiffness matrix and the force vector can be given as this. Again, here stiffness matrix is nonlinear, so we'll use Newton's method, and also I have used arc length method in case of instability. So let's see some numerical example in this case. This is a hyperboloidal cell. For Neo-Hookean material, it is, in this case, it is compressible Neo-Hookean, and all the geometrical parameter and material parameters are given like this. And it is getting pinched in one direction and pulled in the other by the point force. So due to symmetry, we only consider this 1/8 of the geometry as computational domain, and we analyze it by we use the spectral element. So the deformed shape is like this. So here I have compared for two material model. Since it is a very thin, both these material model will give similar result for a very good reason, because because of the thinness of the cell, it is a small strain, large rotation problem, and that is why we know that all material model for hyperelasticity converge to like linear elastic modeling for small strain. So that is why this I think that is my best guess. That is why the result are for both the model are same. But in this case also we see if the order of approximation of a spectral element is lower, the result is not very good. Convergent result we can get by higher order spectral element. These all are for same number of nodes. So there is another one. This is a tubular structure. This is analyzed by cell theory, and here we have the mesh. And under again internal pressure and deform shape. So here in this case also we have compared. This is little bit thicker, so both compressible Neo-Hookean and Saint-Venant are different results. In this case, we have analyzed a circular arc shape cell stripe, and this will show instability. Hence, we have used arc length method to trace the equilibrium path. So this two kind of boundary condition is used. One is pinned and one is completely fixed. So let's see for the fixed boundary condition. Here in this case, this is the different shape at different loading, and here is the path. And for different approximation order, we see that it is getting converged. If here for hinged boundary condition, and again here we see that for increased approximation that it get converged. So to summarize, in this talk, I have talked about hybrid frame-based curvilinear coordinate system and all the kinematic derivation for this kind of curvilinear coordinate system. This makes the complex tubular structure, mapping of complex tubular structure comparatively easy. And also I have talked about higher order one-dimensional theory for soft material and general higher order cell theory for hyperelastic material for orthonormal moving frame. The salient feature of higher order one-dimensional theory, or sometimes called pipe theory, is that it since it uses the general basis function for cross-sectional deformation, deformation approximation, and also gives a rule for domain transformation, which could be very useful for fluid flow through deformable walls. And in higher order cell theory, again, since it is higher order, we have modeled the thickness stretch in this case, and it removes the Poisson's locking, which is very crucial for soft material or biomaterials. And also we have used orthonormal moving frame. So that is all I have in this talk. And also I'd like to thank my collaborators in this work, Professor J. N. Reddy and Professor Arun Srinivasa. I acknowledge their collaboration very thankfully. And with that, if you have any questions, I will be very happy to